Hi, everyone. Thanks for joining us today. We're just going to wait a couple moments for people to log into the Zoom before we get started. Looks like we're going to have a good crowd today. Just waiting a moment for everyone to jump into the Zoom. Okay, it looks like we've given everyone a good chance. So hi, my name is Courtney Brown, and I'm a Senior Marketing Manager here at EDB. I'll be your host for today's webinar, Best Practices in Security with PostgreSQL. I'm joined by Dave Page, VP and Chief Architect, Database Infrastructure at EDB. Before I turn it over, I'm going to go through a few housekeeping items. This presentation is being recorded. We'll be sharing the recording along with the slides after the broadcast to the email that you used to register for the webinar. All of your lines are currently muted. If you have a question, please feel free to submit it in the question panel. If we have any extra time today, we'll be sure to do some Q&A. And with that, I will hand it over to Dave.
Thanks, Courtney. Hi, everyone, and welcome. As Courtney mentioned, my name's Dave Page. I work here at EDB in our CTO office. I've also worked on PostgreSQL since around about 1998. I'm one of the core team members, lead developer at PGAdmin, and also involved with a couple of our non-profit organizations. So, our agenda for today, I'll give a quick introduction to EDB just so everybody knows who we are. We'll look at some of the aspects of data security that you might need to consider. We'll move on to some general recommendations, framework and the focus for today, which will be primarily around authentication, authorization and auditing, and then followed a little bit with some information and discussion on data encryption. We'll summarize that and then we'll have some time for Q&A at the end. So who are EDB? We've been around since 2004. I joined on the very first day in 2007, which was probably about a year after the company came out of stealth mode. We've made lots of contributions to Postgres over the years in the database server itself, as well as things like the PGAdmin project and contributing to the infrastructure and the non-profits and conferences and things like that. In 2007, probably around the middle of 2007, Second Quadrant was launched. They also contributed in many of the same ways that EDB did. And you may well be aware that in 2020, EDB acquired Second Quadrant, making us now the largest by far Postgres company, or dedicated Postgres company there is. We have more Postgres experts on the team than I think than any other company does. So we have over 300 engineers and technical people within the company focused on Postgres and surrounding technologies. It says we've got 26 Postgres community contributors and committers, including founders and leaders. I'm not 100% sure how accurate that 26 number is, but it's certainly quite a few, if not more than that. Michael Stonebreaker, who's the original father of Postgres at UC Berkeley, is one of our advisors. We have Bruce Momjian, who's Peter Eisentraut, who are both fellow core team members on the team, as well as Mark Fournier, who was previously on the core team, but is the other co-founder, as well as some other major contributors such as Robert Haas, Simon Riggs, and many more. Let's talk a little bit about data security. There are various different aspects that we need to look at. Unauthorized access, or what we might think of as what results in unintentional or possibly intentional, depending on whose perspective you have, access to and corruption of data. So that'll include things like data breaches, people hacking into the system, that sort of thing. Data corruption. So this is what may come about if there are software bugs, which thankfully are pretty rare in Postgres. You might also have hardware issues, RAID controllers not working right, networks going down that somehow cause some sort of data corruption. Also loss of access. So if your entire server goes down, you lose encryption keys, somebody pulls the wrong plug in the data center, for example. So these are all different aspects of data security that we generally need to take into account. We're going to focus on the left-hand side today. So primarily on the security measures that you can take to protect your data from unauthorized access or modification. Let's start with some general recommendations. So first of all, and I cannot stress this enough, and it's amazing how often I've seen people not do this. Keep your operating system and your database software patched. Now, if you're running Red Hat or Debian, you will probably know that they're incredibly strict when they release updates to RHEL, for example, or the Debian. They don't generally throw out major upgrades to software. So you won't get Postgres 13 installed when you previously had Postgres 12, for example. They're very strict about making sure that only bug fixes get added with the updates. And Postgres is exactly the same. When you install a major version of Postgres, such as Postgres 12, version 12.1 is an update to version 12. But you can be assured it never includes new features. It's only ever bug fixes or security fixes that are deemed serious enough to warrant an update to the database server. And both the Postgres community and EDB, and not to mention the Debian project and Red Hat and other vendors like those, take this very seriously. It's what we always say to customers, it's better to upgrade your software than not to. I've seen a number of customers in the past that make a mistake. They validate their application on, say, Postgres 11.2, and then maybe they hit a bug and say, well, we can't upgrade because we validated against 11.2. So they stick on 11.2, knowing that there's a potential security issue. But actually, the whole system has been designed to allow them to not have to do that. If they certified their application against Postgres 11 without any suffix on there, then they could freely update and take advantage of the security fixes and other bug fixes that they would get without any risk to their application compatibility. Don't put a postmaster port on the internet. So the postmaster is the listening process within Postgres. It's what's listening for incoming connections. There is almost no good reason ever to put a postmaster port directly on the internet. If you're deploying an application and it's all in one server, then use local sockets on that server, or if you must connect over TCP/IP, use the loopback address. If you're using cloud environments, use a virtual private cloud with a subnet and put your application server and the database server tucked away in that VPC, so only the application server can actually reach the postmaster port. Isolate the database port from other network traffic. So similar to what I just described with the use of a VPC, you might consider using virtual networks on your Ethernet switches, for example, or a different subnet, and just keeping that database port and the resulting traffic away from the rest of your systems. what it's quite common to do in a data center is actually use, for similar reasons, use an entirely separate virtual network for management. So for connecting to out-of-band management adapters on servers and so on. Treat your database in the same way. Isolate it from everything else as much as possible and minimize access. Grant users the minimum access they're required to do their work and nothing more. So the principle of least privilege. If you give people more access than they need, then there's a greater footprint for a potential attack on the system. Give them exactly what they need and no more to absolutely minimize the ways that somebody might be able to successfully attack that system. Now, it's worth noting that that isn't just a security feature. It also can help prevent users from accidentally breaking things unintentionally as well. Restrict access to configuration files. So make sure that only the system administrator that needs to be able to configure Postgres, or the DBA that needs to be able to configure Postgres, can actually modify files like postgresql.conf and pghpa.conf. Set up the security on the system level of your server such that only those people can get to those files and modify them in any way. Now, pghpa.conf in particular, it defines the rules for accessing your Postgres instance. So if you can edit that file, you can open up access to the database to anyone that can connect to the network port. So it's really important that you keep these files with minimal access granted only to trusted individuals. Disallow host system login by the database superuser roles. So don't let the Postgres user on your database or on your server that the database is running under be able to log into the system. There's generally no need. And it's what tends to happen in environments where I've seen that done before is you've got multiple team members that are using that Postgres login. So you have no audit trail whatsoever. Use individual logins for your system administrators. They log in with low privileges, use tools like sudo or sudo to gain privileges as and when needed only. As I mentioned, provide each user with their own login. Don't rely on your application to prevent unauthorized access. So we've got a complex system in Postgres that allows you to manage access controls to objects. It allows you to manage the network access to the database server. And it allows you to implement things like business rules. You know, you can use foreign keys, check constraints, and so on. And in the same way as you might use those foreign keys and check constraints to enforce the business rules that your application is working to, make use of the database to secure the data as well as the application. We'll talk some more about some of the ways you can do that later on. Most important of all, keep backups. Now, I'm sure everybody has backups, but does everybody have tested backups? There's a colleague of mine in the Postgres community that likes to say, if you've never tested your backups, then you don't have backups. And he's absolutely right, because unless you've got a tested recovery plan that has proven that your backup process can allow you to recover that database, you don't really know. You might have a reasonable idea, but you don't know for sure. You might have missed something in the backups. You might have a typo in the script that you've just not realized is there. If you go back to the old school way of doing things, which I know some people still use, you might not realize that the tape is worn out. So always test backups. And this is not just a one-time thing. You know, you should be doing this every week or few weeks at the minimum. Just making sure that you can test the recovery both via backups of the database and the entire system. So we typically have multiple layers of security in the system. I tend to think of this as kind of an onion, if you like. So we have the database itself, of course. We can use data access controls to manage access to that data. So ACLs or access control lists on tables, columns, and so on. Row level security to secure certain rows in the database. Views to allow users to see information that they otherwise wouldn't be able to see. And security barriers, which can provide more protection where you need it. And again, we'll talk about some of these things some more later on. We can also use data encryption at this level, so we can encrypt individual columns of data within the database. So the database itself consists of multiple database files. So at that level, we might have encryption of the file system that those files are living on, for example. So on a Linux system, you might be using LUKS encryption. That, along with the data encryption in columns, is probably going to be tied into a key management system at some point. If you've got your security keys on the same physical system as you've got your database with all these encrypted file systems and columns, that might be a weakness, because if somebody manages to steal the entire system, they've walked off with the encrypted data with the keys all nicely stored on the same box for them. So you may have some external key management system to look after that. We then have the database server itself. So the various things that we can think about here. So the network access that we've spoken about a little bit already. Authentication, so users using different roles. In Postgres used to use the concept of users and groups. Back in, I think it was about Postgres 8.1 or somewhere there around, we implemented the SQL standard roles. And roles can have either a login, well, they have a login attribute that can be set to true or false. If the login attribute is set to true, then you might consider that a user. If it's set to false, you might consider it a group. So they're very similar, but you might hear Postgres people talking about users, groups, and roles, whereas roles are just really this combination of those two concepts. Password profiles we'll talk about a little bit in EDB Advanced Server. We can also do auditing of SQL, so DML and DDL statements can be audited. That doesn't necessarily prevent something occurring or prevent an attack, but it at least helps us later on understand what was changed and who changed it, and maybe try and track down where the weakness in the system was. Data redaction and masking is sometimes important. For example, preventing users from seeing social security numbers, for example. And Sql Injection Attack Prevention. Again, we'll talk about this some more later on. But there are ways that we can try and protect within the database server against SQL injection. Now, that, of course, doesn't mean that we shouldn't make sure our applications are not vulnerable as well. Absolutely, that should be the first thing that's done. But there's some additional security that we can layer on against that particular threat vector. We then have the physical database server host, access to the host. So who can get into the data center? Who can access the cage or the rack that the server is physically in? Then the data center itself. Who can get into there? You might be able to get into the data center, but you may not be able to get into the rack that the database server is actually in. So all of these are layers to the security, and some of these layers have other layers that go around them. The network access, for example, will have layers like the pghpa.conf file. the firewall rules that you've got, the physical network structure, the virtual network structure, and so on. The last thing that we need to look at is the encryption in transit, i.e. making sure nobody can eavesdrop on our users talking to the database or talking to the application. So this diagram could be redrawn in a couple of different ways, but for simplicity, we've just shown it with the user talking directly to the database. Obviously, there might be an application in the middle there. But we need to secure that communication because often that might be happening over the internet, for example. So we need to make sure that nobody can listen in. So for the focus for the rest of the session today, we're going to look at the access to the database application, access to the data contained within the database, and securing the data stored within the database. We tend to look at these through what we call the AAA model, AAA model. This is a very common model that's often used in security architectures. So first of all, we have authentication. So this is making sure that the user is who they claim to be. In the most simple terms, it's a username and password. It might be a username and password with a second factor of authentication, such as a code you need to type in from your mobile phone, or something you have to click in an email, for example. We need to understand who the user is before we can figure out what they're actually authorized to do. And we need to be certain that we know who that user is. Once we're certain, then we need to figure out what they're actually allowed to do, the authorization phase. Is this user allowed to modify data in this table? Is this user allowed to even see data in this other table? That sort of thing. Then finally, auditing, or accounting as it's sometimes called. Record all the relevant database activity and make sure that we include usernames and timestamps in log files. This, as I mentioned before, it doesn't really prevent anyone from doing anything that they shouldn't do, from hacking into the system, for example. But it gives us an audit trail. It helps us understand what they did when they were in the system, and it might also help us trace back to through the vulnerabilities that let them in, so that we can improve our security setup in the future. Let's talk a little bit about authentication. So in Postgres, this is defined in the hba.conf file, pghba.conf. There's actually a typo there, sorry about that. It's critical you should understand this file and how it works, and make sure it's protected against unauthorized modification. Postgres will read through the pghba.conf file when there is a new incoming connection attempt, and it will act with the directives that are on the first line that matches the connection attempt. So what it's going to be doing is looking at where your connection is coming from, what your username is, what database you're trying to connect to, and various other things. And each line in the file describes those things and then specifies an authentication method that should be used for a connection. So the first match it finds in the file defines what type of authentication Postgres will try and do. There are various different authentication mechanisms that Postgres supports. This list is not all of them. There are some more that I haven't listed because they're not very widely used. Kerberos, or GSS API, single sign-on, is very common in high security environments. It does require you have a Kerberos infrastructure set up, but it works very well. It allows you to do logins to Postgres with no authentication that interrupts the user at all. Generally considered to be very, very secure. Sspi is the Windows equivalent if you're running a Postgres server on Windows. It's largely the same. Windows domains are basically built on top of Kerberos with Ldap, with a few Microsoft-isms thrown in. But Sspi works very similarly to Kerberos, GSS API. and allows the single sign-on. So you just connect to Postgres, it authenticates you in the background as long as you have a Kerberos ticket or you've logged into your Windows domain. A lot of users will use Ldap. So what happens with Ldap is Postgres will take the username and password that the user specifies, fire them off at the Ldap server, and the Ldap server will say yes or no. Now, generally, I would advise, if at all possible, use Kerberos, not Ldap. And the reason for that is that with Kerberos, Postgres never sees the end user's passwords. So you can be sure the passwords are never going to get leaked in any way through a Postgres server. Whereas with Ldap, the Postgres server does see those passwords. Now, in normal usage with Postgres from either the Postgres community or from EDB, that doesn't cause any problems. You know, there's nothing in there that's going to log those passwords or anything like that. But you want to protect the system in layers. So even though there is no known threat, you want to protect against it anyway, just in case there is one in the future, i.e. An attacker manages to modify the Postgres binaries on the server such that it can then log the passwords. Very unlikely, but it's pretty easy to prevent that being an effective attack regardless. I've mentioned Radius there. You'll notice that's crossed out. Do not use Radius. Radius was around in Postgres probably 20 plus years ago. It has weak encryption by today's standards, and it uses MD5 hashing for credentials. So avoid using Radius if you are at all tempted. Certificate authentication uses TLS certificates, often known as SSL. These are typically used mostly in machine-to-machine communication, so for your application server to talk to your Postgres server. But in some environments, users do use them to log in and connect as well. MD5 and Scram use usernames and passwords that are stored actually in Postgres in its own internal system tables, system catalogs. Avoid MD5. The Scram has been around now since, well, probably 4 or 5 years at least, and it uses much more secure hashing than MD5. And in fact, I think as of Postgres 14, Scram now becomes the default over MD5. You can also use those mechanisms with password profiles in EDB Postgres Advanced Server, and we'll look at that shortly, like now. So this has been available in Advanced Server 9.5 and above. This is not functionality that you'll find in PostgreSQL. This is basically Oracle compatible password profiles. So you can specify the number of allowable failed login attempts, whether or not an account should be locked. You can mark passwords for expiration and so on. So there are various things that allow you to secure or more securely use passwords. Now, these are really only relevant, obviously, if you're using Postgres's internal password management. If you're using it Postgres with Kerberos or something like that, then all this would be handled by the Kerberos infrastructure for you. But for smaller deployments, this is often the way people would want to go. Pretty easy to set up. So we can create a profile, first of all, and then we can create a user, and then we can assign that profile to the user. So the alter user, my user profile, my profile. And with a pretty straightforward select query, we can look at what profile is associated with a particular user. We need to define some rules to make that profile actually do anything useful. So here we can see an example where we're setting the failed login attempts maximum to 3 and the password lock time to 2. And again, we can then go look at the system catalogs and see what the current status for that user is. Now, after a first failed login attempt, if we run that same query again with this profile applied, we'll start to see that the role failed logins column has recorded the failed login attempt. But at the moment, the role status is still open, so it's still available. After a few more user failed logins, 2 more, at that point, you'll see that the user account becomes locked. And in this case, it's timed, so it's going to unlock itself at the time in the role lock date column plus whatever the lock time was. If you need to override that, it's very easy to do. The super user can do alter user my user account unlock, which will just unlock that again and allow the user to log back in. So the next part of our AAA model is the authorization. So at this point, we know who you are. Postgres has used whatever authentication mechanism it needs to authenticate you. Once we've got that information, we need to figure out what we are going to let you do. So very simply, we're going to start by managing access to the privileges, or managing the access privileges or ACLs to tables, views, and other objects in the database. Some best practice considerations: revoke create privileges from all users, grant them back to trusted users only. There is generally no reason, particularly in a production application, why most users who might be able to connect to the database should be able to create things in it. The DBAs, obviously, they might need to, but if you've got people that are connecting with tools using ODBC drivers or that sort of thing, JDBC drivers, and running reports through reporting tools, there's no reason why most of those users should ever be able to create something. Secondly, don't allow the use of functional triggers written in untrusted procedural languages. So Postgres has a very rich set of hooks that can be used to extend Postgres, and one of the ways that you can extend it is by writing procedural languages. These languages can then be used when you run create function or create stored procedure to define the actual body of those functions. This is very powerful, so it allows you to write functions, stored procedures, and triggers and so on in languages like Perl, Python, and Tcl. Some of those languages are what we call untrusted in Postgres, and what that means is they don't run inside of a security sandbox. So some languages will be sandboxed by default, so they won't be able to do certain things. You could use the syntax of the language, but you might not be able to read files from the file system, for example. Other languages don't provide a way to allow us to sandbox them. So Python, for example, there's no way for us to prevent a Python function from being able to read the password file in the /etc directory. So don't let users create those sort of functions in untrusted languages. Restrict them to the trusted ones only that will allow them to do things with SQL and do things with data, but not necessarily gain access to the network or to the file system and so on. Security definer functions are very, very useful. So by default, a function or a stored procedure in Postgres it runs with the security of the invoker, i.e. the person that started or ran the SQL. What security definer functions allow you to do is They give you a way of elevating privileges. So when the function is run, it actually is run with the security context or privileges of the person who created that function, of the person that owns the function. That may be a super user, but security definer functions are always created by super users anyway, no matter who owns them. What this allows you to do is provide access to certain pieces of functionality to users that they might not be able to get using their own user account. Understand what security definer functions are, read up on them thoroughly. They can be very useful, but they're also very powerful. And if you misuse them in the wrong way, you could actually open up a security hole. But on the other hand, their proper use does allow you to create much more tightly controlled systems. Finally, database objects should be owned by a secure role. It's usually not a good idea to have the tables in your application be owned by the user that your application server is connecting as. So imagine you have a Django application, for example, it always connects as user web app. Web app should be able to read and write rows in the tables as it needs to, but it should not be able to create those tables or drop those tables. Because if an attacker comes across a bug in your Django application, manages to execute a Sql injection attack, we want to make sure that they can't drop tables. Now, one note here is to be aware when we're using log statement in Postgres in the logging configuration, the alter role command can result in password exposure in the log. So if somebody does alter role Dave, set password foo, then it'll write foo into the logs. So just be careful of that when you're working in these areas and setting up your authorization. In Advanced Server 11 Plus, you can use the EDB filter log redact password command to prevent that happening. And again, of course, it doesn't typically happen if you're not using MD5 or Scram, because you would not be modifying your password using Sql in those cases. So I mentioned earlier row-level security is sometimes in Oracle world called virtual private database. This allows us to restrict on a by user which rows can be seen or updated and so on. Very simple example here, we create a table called accounts, enable row-level security on that table, and then we create a policy that allows us to specify the conditions under which somebody can see a row or update a row or whatever. This is a very simple example here, but there are individual options for allowing updates versus deletes and so on. So what this is allowing us to do in this example is we can work with rows in this table. If the manager of the if the value of the manager field matches our current username. So for example, if the manager field contained Dave and I'm logged in as Dave, then I can work with those rows. If it doesn't, then I can't. Data redaction is often useful when you're working with things like social security numbers. EDB Advanced Server has functionality for doing redaction. You can do this with views quite easily as well if you create access to particular tables through a view to your end users. And in fact, Postgres actually has an example of this built into its system catalogs. The system catalog that contains the role names and role passwords is only readable by super users by default. However, there is a view that sits on top of it that allows regular users to select from that table, but it will show the password masked out, so thus not leaking any password information. Auditing. So PostgreSQL doesn't have an audit module as such. There are a couple of third-party add-ons that you can use, but Advanced Server does have auditing built in. In Postgres, you're pretty much limited to just logging DML and DDL queries as well as connections and disconnections. But Advanced Server gives you a dedicated audit log where you can track all sorts of SQL activity, such as DDL, DML, and different types of SQL statements, and so on. All of that goes into a separate log that's independent of the regular operational log that Postgres will keep showing errors and things like that. That's definitely something that's worth looking into when you're figuring out how to deal with auditing in your system. There's a few configuration parameters available there. You can have your logs in XML or CSV format, for example, so that you can easily read them from other systems. You can specify the directory and file name and rotation parameters. Sometimes logs can get big, so you need to rotate them out. You want to make sure that they're stored in a location that's as secure as you can make it. Then obviously we can specify what type of SQL statements are actually going to be captured in that log. Okay, that's about it for now on the AAA. Encryption. The really important thing with encryption is to understand the threat vector. What I've often heard people say is, oh, we need to encrypt our data. And the first question I normally have back for them is, well, what are you protecting against? And it's really critical that you understand that, because different threats require different mechanisms to protect against them. For example, having full disk encryption and storing your data directory on a file system that's protected with LUX or Bitdefender or any similar products doesn't protect against somebody hacking into the system and reading the data from the disk, because it's up and running. The disk encryption key has already been entered, so the kernel has decrypted or is decrypting the data as it read. The threat vector that full disk encryption is protecting against is somebody physically stealing the drives. In that case, obviously they've stolen the drives, the system's shut down, there's no key on the drive if everything's set up right. So there's no way they can get to the data in that drive. So that's a very different threat to protect against than, say, a man-in-the-middle attack on the network. So it's really key that you understand what you're trying to protect against. And obviously that might be multiple different things. If you're storing passwords, for example, then they obviously must be hashed if you've got user passwords for your application in your database. There are a very, very narrow set of circumstances where it might be appropriate to encrypt rather than hash. You may remember that hashing is a one-way process, whereas encryption is two-way. That is, you can extract the original data again if you know the key. If you think you have a reason to encrypt any passwords that you're saving, you need to be very careful that you build that system in a secure manner. So my general advice is, don't do that unless you really, really know what you're doing. You might want to encrypt specific columns of data. So, for example, you might be storing credit card numbers. as part of your application to allow users to quickly make purchases a second time. So you may need to encrypt that specific column in the database. You might need to encrypt the partition or the disk, as I mentioned, I was talking about at the beginning with the example of somebody physically removing the drive. Passwords across the network, data across the network. As a sort of added bonus, if you're using SSL or TLS, then you might actually also be using that mechanism for doing the host authentication. So that may be where your application server is talking to a database server. And any client-side encryption that may be required. So Sql Injection Prevention is another area that we need to be very wary of. So this occurs where your application is designed in a way that allows the attacker to provide inputs that then affect the SQL that is run on the database server. So very early applications that were written often suffered from this because people weren't aware of the problem. There is a very well-known XKCD cartoon that I've shown there, which illustrates this problem fairly well. If you hear database people talking about little bobby tables, they're almost certainly talking about Sql injection attacks. So to give an example, if you consider a website which will log in a user, if you construct a query just by concatenating pieces of SQL with input from the users together, it's very easy for an attacker to inject something in there. So for example, by crafting the password I've put in, I've added this OR clause that will be evaluated. So if I'm checking that I'm actually getting a non-zero value back from that query, I'm always going to get at least one because I've said OR 1 equals 1. That's a tautology clause. To fix that, we need to make sure that our user input is sanitized. But we shouldn't be doing that ourselves. There is functionality in the database and functionality in the database drivers to do that for us. So with PsychoPG2, for example, which is probably the leading Python driver for Postgres, we'd construct that query and execute it much as is written there. So we replace the actual values with %s in both cases, and then we've provided the username and password as a tuple of parameters. What PsychoPG2 will do is then use correct and safe methods for substituting in those values and execute the query. So it doesn't matter what is in the password there, it will never get executed as SQL. Now, one other thing that you might want to consider if you're using advanced server is we do have a module in there called Sql Protect. And whilst this is absolutely no substitution for building the code right in the first place, it does provide an additional layer of security. What Sql Protect will do is it can prevent DDL commands. It can figure out if there are tautologies in the SQL and deal with and block various other potentially bad SQL queries. It also has a learn mode, so you can run it in learning mode and it will learn what your application does. So it will figure out if your application, when it's all of a sudden starts using a table or a view that it doesn't normally use, it can block that and leave you to then figure out what was going on. And obviously you can modify the configuration to allow it if it was legitimate and it just wasn't something that was learned during the learning session. Or it may be that it's actually blocked an attack. So that brings us pretty much to the end of the discussion here. Security is a huge topic. There are various resources on our website. Obviously, what I've given you here is just an overview. The first blog up there, actually that one I don't think is a blog, I think that's the actual documentation, is what's known as a STIG. So the STIG is a standard way of deploying Postgres that's, I believe they come out of the US Department of Defense. So it's the process for deploying Postgres securely to their standards, which can be useful. The second one is a blog that I wrote. It was, to give you an idea of how long it was originally a set of 5 quite long individual posts in a series. They've all been combined together into one, so it's a little bit longer than your average blog, that one, but it goes through from end to end what you should look at within your deployment. So some of the things that we've spoken about today are in here, or most of what we've spoken about today is in there, but it goes into more detail and takes you right through from one end to the other, how you might review and assess your deployment. And then there's a number of other blogs on working with password profiles that may also be of use. So that was all I had for today. Thank you very much for listening. I think there were some questions in the Q&A panel.
Yes, one question came through. They wanted to know if you could talk about what features are available in community Postgres versus EDB advanced server.
Okay, well, I can't really go through everything that was in community Postgres beyond what I've done, because that would take far longer than we have, unfortunately. I think I called out fairly consistently when things were just in advanced server when we were going through a moment ago. So password profiles, Sql Protect, the audit, logging are the main ones that spring to mind. Advanced server also does have some virtual private database functionality that's more Oracle compatible, but it's built on top of what Postgres does with row-level security. So that will be more of interest if you're coming from an Oracle environment. I don't think it really necessarily adds any functionality that's not in Postgres. It just does it in a different way.
We also had a few people asking about the presentation and the recording. So we will be sending a recording along with the slides after the fact to the email you used to register. So look out for that either later today or first thing tomorrow. Let's see if there's any other questions that we might be able to handle. Someone's wondering what procedural languages are trusted. I don't know.
Oh, that's a good question, because off the top of my head, I couldn't tell you exactly. So so SQL is trusted, and PLPG SQL, of course. C is not trusted. Python is not trusted. I believe Perl has a trusted version, and possibly Tickle. Other than that, there are lots of other procedural languages available, but those are the ones that are actually in core Postgres. The rest are all third-party add-ons. So there might be other open source projects, and I don't know about any of those.
Okay, well, we're getting right to the top of the hour. There were a lot of other questions that came through that were more specific, so we'll take those offline, make sure we get the answers and follow up with all of you. But thank you all for joining us live today. Thank you, Dave, for presenting, and we all hope you have a great rest of your day. Thank you.
Thank you very much.